Hello everyone. In this session, I'm going to talk about clustering, which is a part of unsupervised learning, right? We have looked at different kinds of supervised learning techniques till now. Under the supervised learning, we said there could be classification problems, there could be numerical predictions, and in some cases, we can have some kind of algorithms which can cater to both of them. Under the classification, we have looked at Nave's Bayes, the nearest neighbor algorithm. We have looked at decision trees. We have also looked at classification rules. So these are the ones which cater to the classification problems. Similarly, we have looked at the linear regressions. We looked at regression trees, model trees, which are falling under the numerical prediction. Similarly, we also had the support vector machines as well as neural networks, which can be categorized, which can be utilized for both classification as well as the numerical prediction kind of objectives as well. So, all these are supervised learning. In the unsupervised learning, we said there are two major aspects. One is clustering or grouping the data. The other one is pattern recognition. So two major aspects as a part of unsupervised learning. So out of that, right now I would be looking at the clustering aspect, where there is no target because it's a unsupervised learning. We are trying to identify the similarities between the groups, and based on that we are trying to cluster the data based on various features. Cluster as a word itself is group. So we are trying to find the natural groupings in the data. That is what is the objective of clustering. So we will try to understand what do we mean by clustering here. As a machine learning task, how do we treat clustering? One of the oldest and the most powerful algorithms, one of the very old kind of algorithms pioneers in terms of clustering is the k-means algorithm. So let's see how do we really use k-means clustering algorithm for doing the clustering of the data. And so to say which variables are close, or to see which examples are closer and which of them are farther from each other, there is some level of distance measurement that we talk of. So how do we use that distance to really assign a variable to a particular cluster versus assigning it to some other cluster? So to whichever cluster a particular example is closer, it would be assigned to that particular cluster. And after that, there is again a revision of the process. After once the whole assignment is done, there is a revision of the process also that occurs. So we will have to see how that assignment and reassignment typically occur. How do I really decide on how many clusters I should go with? And once I do all this aspect, I'll take an example. Once we have a theoretical understanding of the whole process, we can take a data set, and on that data set we can very well perform a clustering process. So as it is very clear, it is an unsupervised machine learning. So there is no prediction aspect. I am not doing a classification or any kind of prediction here. So it's an unsupervised learning. So we are dividing the data into clusters here. The whole data that is supplied based on the various features associated with the data, we are grouping the data into different clusters. So there is no prediction aspect here in the process. It is primarily used for knowledge discovery. I am trying to come out with some kind of a new pattern in the data. So there is no relationship between the dependent variable and the independent variables here, because there is nothing called a dependent variable. So there is no relationship between the dependent and the independent here. All the variables are taken together, and depending on how close they are or how farther they are from each other, they are grouped into the appropriate category. So we are trying to form natural grouping rather than looking at the groups of the dependent variables. We are trying to see the natural groupings within the data, right? And the main fundamental behind this clustering aspect is the records that are there, the examples that are there within the cluster, right? The examples that are there. Now let's say here this is the whole data, right? Now I'm talking about one cluster, two clusters, three clusters. So the examples that are there within the cluster, they all should be very much similar in many aspects. Whereas if I'm talking about the elements between the clusters, they should be very much different from each other. So within this cluster, all of them should be more or less similar. Within this cluster, all of them should be more or less similar. But between these two clusters, the characteristics of the element should be very much different. So all those which are having similar kind of characteristics, which are more or less related kind of elements, related kind of records, related kind of examples, I am placing them together and I am separating them from the other groups of examples. So that is what is going to happen as a part of the clustering process. Coming to the major applications, yes, the marketing guys use them very heavily. They do the segmentation of the customers. So based on the buying patterns, I want to group the customers. Depending on the demographics, I want to group the customers, so that once I am able to bifurcate my total customers into different groups, I can target a particular campaign to particular group of customers. So that's how we can very well use the concept of clustering. Even if there are some anomalous behaviors, right, all the majority of the elements are going into one or two clusters, but one or two abnormal data points, they are going into some other clusters. So we are able to identify the abnormalities in the data, those records which are quite different from the rest, and we can very well try to correct those abnormalities and anomalous behavior in the data. And if I have large data set with huge number of values, so we can very well group all those features and we can very well reduce the number of categories that are there for this particular data. So even if for reduction, the whole dimension reduction, the data reduction, I can very well use the cluster analysis also. So generally when I have fully diverse and varied data, and where my objective is to reduce all that data into a few groups, group the data in such a way that overall this whole data of few thousands or few millions of records are coming down into a countable 5 to 10 groups of data altogether. So this is where the clustering will have a major role to play. But once the clusters are formed, I have to create a meaning. Cluster in itself does not have any kind of a meaning. So I have to really see what is the meaning that I can create to this cluster. How do I give a name to this particular cluster? What is the major differentiator of cluster 1 and cluster 2? In what aspects is cluster 1 different from cluster 2? So I have to give the meaning to it. So I have to really see that whatever the clusters that are getting formed, they have some kind of business meaning or functional meaning, not just a technical way of dividing the clusters. So when it comes to clustering, there is a new data creation that is occurring, because the cluster numbers, we don't have any kind of a target variable, but the cluster numbers are identified and a new data is created. It's not that I'm mapping, there is no mapping between a class and the variables that are determining the class. Here there is no class at all. I am creating the class. So clustering is creating the new data. So if there are new variables that we are talking of, the cluster, the label is given to those variables, to those examples, based on the relationships within the data itself. So there is no formula, something like that. So based on the whatever the pattern I have identified within the data, based on the proximity of the various elements within the data, so the cluster grouping is typically given to them. So it tells you which group of examples are closely related, which group of examples are very much farther away from each other. Now, how do you really analyze it? What is the kind of meaning you give to it? What is the kind of action that you are going to take with these clusters? How are you treating C1, C2, C3? For what purpose you want to use C1, what purpose you want to use C2? All these kinds of things is purely up to the analyst, right? So basically it's like, instead of we doing the classification manually, instead of we doing the groupings manually, which could have a lot of subjectivity, when I am using the machine learning to do this job, I am expecting that this grouping of the various elements into different groups happens more and more objectively, rather than any kind of a subjectivity being attached to it. So it clearly looks at how closely the examples are related, and if they are more and more closely related, they are assigned to homogeneous groups, and if they are very much farther away from each other, they are put into a completely different group. That is how the clustering typically works. Now, there are so many algorithms that are there for performing this job of identifying which elements are closest to each other, which elements are farthest away from each other. There are different ways of doing them, but one of the most popular ones, very commonly used one, is called as the k-means clustering algorithm, and which is kind of a pioneer in this clustering process. Of course, after that we have got various other techniques that came up in the world of clustering, but yes, this is the base for majority of the new clustering algorithms that came up. So looking at the goodness of this algorithm, so the concept that it is using, the process that it is using for creating clusters, for grouping the examples, there is no statistics that is involved in it. So the clusters are formed using simple set of rules, and there is not too much of statistics that is involved in the process. And there is a lot of flexibility. So lot of things can very well be addressed, lot of problems can very well be addressed, lot of shortcomings can very well be addressed by doing some kind of small modifications to the data. And what we see is, it is very good at dividing the data into useful clusters. We'll see with our example also, but what we can very well say is, this particular algorithm is comfortable enough in terms of dividing the data into good number of useful clusters compared to many other algorithms. But of course, it is less sophisticated. Nowadays, more and more sophisticated algorithms are coming into picture. But of course, they do clustering slightly differently. But the end objective is group the data. So even this as well as the others, they are grouping the data. There is no one single method which says that this particular algorithm is better than the other one, or it is worse than the other one. The only thing is, the more and more meaning I am able to derive from my data, that would be more preferable for my classification purpose, right? For my grouping purpose. So there is some kind of, the way it uses some kind of a random chance, which means the initial, when we look at the process in the next slide, you'll come to know it actually uses a mechanism where it identifies the initial clusters. It identifies the initial clusters, and this identification process is done on a random basis. So because of that reason, it is nowhere guaranteed that it will get only the optimal set of clusters. Depending on what is that initial cluster that has been generated, you may or may not get an optimal set of clusters. So that is where we use the word as local optima. So we may get a local optimum kind of cluster, but we may not get a global optimal set of clusters. So we also need a reasonable guess. How many clusters do I need to go with? 3, 5, 10, how many clusters I need to go with? Obviously, just like with many other algorithms that we have done till now, I can quickly play around with what is the two cluster solution, what is the 3 cluster solution, what is the 4 cluster solution. I can very well try out different kinds of mechanisms by changing the function a little bit, but I can very well see in which kind of classification the meaning is coming more and more appropriate to the clusters. So in the whole thing, all the examples that I have, all my data that I am taking, it is assigned to one of the K clusters. So initially we have to specify how many clusters do I require. Let's say I have specified that I require K clusters. Then it will assign all the examples that I have to one of these clusters. The way it assigns is, it tries to minimize the differences within each cluster. So within each cluster, they have to be very close, very much closer, and it tries to maximize the distance between the clusters. So within the cluster, the differences are very, very minimal. They are close enough. Whereas between the clusters, the differences are much, much wider. That is the major funda that is being used for doing the classification process. So if I am looking at K and N is the number of examples, K is the number of clusters. If both of them are very, very small, then I can look at optimal clusters. But if they are very, very, if they are slightly larger also, it is not possible to come out with an optimal combination, because if they are very small, yes, I will get clear differences. I can allot each of the n data points to each of the clusters quite comfortably. So what we really need to see is, the algorithm typically uses a heuristic process. So initially it starts off with a local optimal solution itself. So there is an initial guess. Okay, so initially 1, 2, 3. If I am talking about a 3 cluster solution, 3 random examples are picked up as 3 different clusters. Now the 4th one, it will see which cluster is closest enough, right? Which particular one is closest enough. Is the 4th one closest to the 1st, 2nd, or 3rd? Now if it is closest to the 1st, it will put this example into this particular cluster. So initially it starts with a guess. 1, 2, 3 are purely based on guess, and then modifies the assignment slightly to see if the change improves the homogeneity. So initially the first step is allot the elements in this way to all the clusters, but after that, based on the element that got allotted to each of the clusters, try improving the cluster center, and again repeat the whole process, seeing if there is any kind of a transfer that is happening of different examples from one cluster to the other. So you could see now the process wise. So we have initial set of K clusters. Initially you assign all the examples to this initial set of K clusters. So depending on the distance. So whichever cluster is the closest enough to the new observation, new example, so try to push it into that particular cluster. So that's the first step. Once all the examples are assigned, now you update the assignment. So basically now what has happened, initially 3 clusters has been taken. So it might so happen that 4 is here, 5 is also here, right? 6 is also here, 7 came here, 8 is here, 9 is here, 10 is here. Like this, different records, examples got classified into different clusters. So this is the first step. Now the assignment is updated. Now here we have 1, 4, 5, 6. Here we have 3, 8, 9. Here we have 2, 7, 10. So now you update the cluster center. So we are adjusting the cluster boundary now based on the example that are falling into this cluster. So I am typically computing the new cluster center for this group, new cluster center for this group, new cluster center for this group. So now these will become my clusters, cluster centers. Now what I can do, I will see whether each of these elements individually they are closer to this cluster center or this cluster center or this cluster center. So because of this there is a possibility that it might be better that if I classify it into this particular cluster rather than this cluster. So there will be some kind of reassignment that can happen because this cluster center got changed now. Because the cluster center got changed now, there is a possibility that some kind of transfers can very well happen between the groups. So this kind of transferring, reassignment to the different clusters is going to happen in an iterative fashion until the cluster centers are in such a way that no more movements are possible. And that is when the finalization of the clusters is going to happen. So this is what is the way the k-means algorithm works for determining the clustering. Now I have already talked about how the distance is being used. Here the distance that is being used is an Euclidean distance. We have already discussed about the Euclidean distance, which comes out as x1 minus y1 whole squared plus x2 minus y2 whole squared plus so on. So this is the kind of a distance that we are measuring, which is what we are calling as a Euclidean distance. And wherever between the 2 points or between one record and the selected cluster. So for all the clusters 1, 2, 3, the Euclidean distance with respect to each of these clusters or cluster centers is typically computed, and wherever the distance is the least possible distance, the allotment of that particular example goes into that particular cluster. So k-means treats feature values as the coordinates in a multi-dimensional feature space. So all the features, if there are 10 features that we are talking of for creating the cluster, so they are the coordinates x1 to x10 in a multi-dimensional feature space. So initially, depending on how many clusters I wanted, out of that n elements, out of that n records examples that I have, k of them are chosen randomly, and those are typically called as cluster centers. Right? So k points are typically treated randomly and they are called cluster centers. So k random examples from the training data set is being chosen. So they are the initial cluster centers which are done on a random basis. The other examples, now so if I am saying I have 10 different examples, 3 clusters I want. So right from the 4, 5, 6, it will see to which cluster center each of these are closest to. And that closest to is actually computed through a distance function, and in this case the distance that is being used is Euclidean distance. Again, there are some algorithms that use Manhattan distance or Minkowski distance or any other different distance kind of algorithm. So we are trying to find out the distance between each example and each cluster. So wherever the distance is coming out to be the least, whichever is the cluster center to which the distance is coming out to be the least, we are doing the assignment of that particular example to that particular cluster. In this context, we are also bringing out Voronoi diagrams, so which are typically nothing but the areas that are closer to one cluster than the other. Now if I am talking about some set of points, probably yes, let's say these three clusters are coming out. So this is the area where this cluster is very much possible. This is the area where you will get selected. If your points are somewhere in this range, they get selected into this cluster. If your points are somewhere in this range, they get selected into this cluster. So this kind of a diagram that we are talking of, the areas where a particular example can get classified into a particular cluster is what we are calling as Voronoi diagram. And there is a place where all the boundaries are meeting. So this is the place where all the boundaries are meeting. This will be the maximum distance from all the three cluster centers. So that would be the initial phase that happens. Now once the initial phase is done, the clusters are now recalculated. The cluster centers are recalculated. They move to a new location, which is called as a centroid. Centroid is nothing but now, okay, these are so many elements that are there in this cluster. After the initial assignment, there are so many examples in this cluster, so many examples in this cluster. Now what we are doing is, we are computing the mean of all the elements that are present in each of the cluster on that particular, on each particular variable. So that would be called as a centroid, right? If there are n different variables, we are talking about finding the center of each of the clusters for all the n different variables. So that is what we are calling as a centroid. And now, so we have one centroid for cluster 1, centroid for cluster 2, centroid for cluster 3. Now the same process is repeated. All the examples again, 1 to n that are there, each one would be compared with the new cluster centers. And because of that, there might be a possibility that this one variable earlier was part of C1, now it can move as a part of the C2. So there is a possibility that examples can get shifted. This is what we are calling as reassignment. So some of them typically move from one cluster to the other. So when there is so again the whole process is iterated. After again the values are moved from one cluster to another, again the cluster mean centroid is typically computed. Again with the newly formed centroid, again the distances are typically measured. So you find that this process of recomputing the centroid and again reassigning the elements to the different clusters, this process happens in an iterative fashion. And when no more points are there for reassignment, this is when the clustering process completely stops, and that is where the cluster alignment assignments are completely reported for each and every example. So we get the cluster assignments, and along with that, even if there is any kind of update in terms of the cluster centers, cluster centroids, even that is also computed and updated. By the way, how many clusters do I need to choose? There is no hard and fast rule, or there is no direct formula which says this should be the number of clusters I should go with. It's a balance that we are talking of, because if the number of clusters is very large, there is a possibility that within each cluster there is a lot of homogeneity in the clusters, but at the same time there could be a problem of overfitting the data also. So that is the kind of trade-off we are looking at. Yes, I require homogeneity, but at the same time, it should not happen that I am overfitting the data, because at a later point when I have to do the groupings accordingly, For the new data, I may not be able to do it at all. So at one point, try to use, if you have some kind of in-hand knowledge, prior knowledge regarding the number of groups in the data, use that as a yardstick. Or in some cases, probably your client himself will tell you how many clusters he really wants. Let's say you are talking about you have 5 managers to do the job. Probably I require 5 clusters so that each cluster will be assigned to a specific manager. So in some cases, my number of clusters could come from such kind of a business requirement also. But again, I'm not going with this bluntly, but there is a rule of thumb which says go with square root of n by 2, depending on the number of examples in the data set. But at the same time, if the number of examples is quite high, let's say 10,000 examples are there or 20,000 examples are there, then we are talking about 20,000 by 2 and square root of it, making it 100 clusters to be created. So sometimes when the data is very large, this kind of classification could be a problem altogether. Generally, we have something called an elbow method, which typically says look at the homogeneity and heterogeneity between the clusters, within the clusters for different values of k. So wherever you are finding that it is getting saturated almost, right? Homogeneity, we see that it is increasing as the number of clusters is increasing. But after a certain point, the rate at which it is increasing is at a very diminishing rate. Similarly, if you see within the group heterogeneity, again it is decreasing because homogeneity is increasing. But again after a certain point, the rate at which it is decreasing is much lesser. So that should be the optimal number of clusters that we would be selecting. But again, to compute that kind of homogeneity versus heterogeneity, we have different kinds of statistical measures that are there, and a lot of tools and algorithms typically have already implemented the elbow method as a part of their implementation process. So we can use that kind of a method to come out with a choice of appropriate number of clusters. So this is the background information that we need to have conceptual understanding regarding the clusters. Once we are comfortable with this aspect, we can very well take up a data set. We'll see, try to find how many clusters we want to group that whole data, and see what is the level of goodness of that particular clusters. Can we really use that clusters for any kind of business analysis? Such kind of things we can really try to look at. All right, now let's look at an example to find the natural grouping among the data. So let me take a data set, right? I'll use the same insurance data that we have used for a lot of prediction algorithms. So I'm reading that same insurance.csv file, right? So we know the structure of it, but let me quickly look at the structure of that data, which is a data frame. Here the factors are only two, fair enough. Here there are two factors. Smoker is a factor variable with no and yes. Region is again a factor variable with 4 variables. So this is the data that we have. So we are looking for any kind of missing values. I don't think this data is having any kind of missing values. Now we have to normalize, either using the min-max normalization or a z-score. And if I have to do the normalization, all the variables need to be integer variables. So it's better that I convert all of them to integers out here. So I can very well say insurance dollar mail. I'm taking a new variable, insurance dollar mail. I'm setting if else insurance dollar mail or insurance dollar sex is equal to mail. If that is equal to mail, we are setting it to 1, else we are setting it to 0. So that's one thing. Then we are also saying insurance dollar smoke, wherein we are setting insurance dollar smoker is equal to S. So this we are setting it as 1, otherwise 0. Then similarly I can very well create for I can very well look at the region. There are 4 regions altogether, so I have to create 3 different dummy variables. So initially let me start with northeast. So wherein I can set insurance dollar region is equal to northeast. Is equal to northeast. Then we are calling it as insurance dollar northeast. Then similarly we are going for northwest. Right, so this is becoming northwest, and here also I would be changing it to northwest. And similarly now I can go with southeast. So for 3 of them I am creating 3 dummy variables, so which means southwest is the the southwest is a default one, which would be zeros for all these 3 variables. Southeast. So we are creating 5 dummy variables altogether, right? And I can remove those factor variables, because now if you look at the structure of insurance, it is okay. All these are numbers, the ones that you have created right now, but there are 3 factors. So it's better to get rid of those factors. So I'll remove the factor number 6, 2, the variable number 2, 5 and 6. I'm removing those 3 of them. So I'll say now insurance is a subset of insurance, wherein I'm taking all the rows, but I don't want the column numbers 2, 5 and 6. So after removing those, this is what is my structure. I'll take the structure of insurance once again, which works out to all of them are either numbers or integers. Now I can very well, I should better remove the charges also, right? Because the charges is a dependent variable, right? I don't want to look at the charges right now. So I want to look at, I will take it into a separate variable called insurance 1, where I am looking at insurance. I am taking a subset, I am taking all the rows, but not the all columns except the 4th column. So I am taking all the rows, all the columns except the 4th column, calling it as insurance 1. So I'll do the clustering based on the insurance 1, and after that let me see if I can really derive some kind of meaning regarding these clusters as far as the charges are concerned. So as it is said, I should do a normalize using a min-max normalization or a z-score, so that the size really does not have a major impact out here. So probably I'll rewrite it into the same variable. So let me call insurance 1 as the scale of insurance 1. So I'm rewriting it into the same variable. So insurance 1 is coming out as the scale of insurance 1. Let me quickly look at the head of what this insurance 1 now is containing. Age, BMI, children, male, smoke, northeast, northwest, southeast. So these are the different kinds of variables that got created right now. Now we are doing a training of the model on the data. So k-means is there as a part of the base stats package itself, which will provide a vanilla implementation of the k-means algorithm. So I can very well use k-means, where I am taking the data, comma k. I have to specify both of them. So model 1, let me call it as model 1, because we'll change the k values as we move. So I will say model 1 is nothing but k-means. Here it is taking the data insurance 1, right? It has taken the data insurance 1 and the number of clusters. Let me go ahead with 3 cluster solution to start with. So I'm saying K means the data and K. So it requires the data frame containing only numeric data. That is where we have converted all of them into numbers, and after that we have done even the z-score of each of those. And I have to also specify how many clusters I want. Right now I have specified 3 clusters. Okay, that's it. My model got created. Let me check the model 1, what it is giving. So there's a lot of information that it is giving. So K-means cluster with 3 clusters are formed. The first cluster is having a size of 324, the second one with 689, and the third one with 325. And now if you see the cluster means, right, 0.004, age wise if you see, positive means it is above average, negative means below average. So now you could see for this cluster, cluster 1 is having a very high age, right? Age is above average. Whereas you could see cluster 3 is very young people, right? If I see here, cluster 3 is, okay, 0.0017 and it's a negative. So cluster 2 is very young people. Cluster 3 is moderately young, whereas cluster 1 is looking like more old people, older ones. And the same way if I am looking at with respect to BMI, cluster 2 looks like people with very high BMIs, right? Their age, they are very young people, but their BMI is very high. Whereas cluster 1 and cluster 3, their BMIs are more or less similar. Whereas cluster 2, so if you look at the cluster 2 characteristics, these are the people who are very young, but they have a very high BMI. And if you look at from a children perspective also, they don't have too less or too high kind of children. But if you are looking at cluster 3, who have a lesser BMIs, who have moderate age, middle-aged people, but have more number of children, and typically more toward the female category, and who do not smoke much, non-smokers. If you look at the location wise, they are not belonging to northeast, they belong mostly to the northwest location, right? They belong more to the northwest location. So those are the set of people that this cluster is getting created, the cluster number 3. So I can really try to identify what are the different clusters and how they are getting created. But if you look at some of the things within the cluster, sum of squares by cluster. So here within the cluster, sum of squares is 1599.469, 4397 and 1477. And the other way of measuring between sum of squares by total sum of squares, it is coming out to be 30.1%. That is the typical measure that is coming out, right? Within the clusters, these are the sum of squares. So I am looking at between the clusters, it has to be as higher as possible, right? Within the clusters, the distance should be much lesser, whereas between the clusters, the distance should be much higher. So out of the total sum of squares, this is giving me that between the clusters, the sum of the squares is forming approximately 30%, right? And these are the cluster groupings that are typically coming out as. Now similarly, if I want to redo this process, calling it model 2, wherein I am increasing the number of clusters, instead of 3, let's say I am going with 4. And I am looking at model 2. And now you could see this is coming out to 35.5. So there are different clusters that are coming out here. So between the clusters, the distance is getting more and more maximized. So this looks like a much better solution. A 4 cluster solution looks like a much better solution for me out here. And in this I could see the cluster 3 are the guys who are having very high age, who have very high body mass index, or who have at least more than average, above average body mass index, who have very few children, females, who do not smoke. So these are some of the things that is primarily coming out as a part of this particular cluster. And we could see that the total, the sum of squares between the clusters versus total sum of squares is 35.5%. Now I can look at still trying to increase the number of clusters. So different cluster solutions are coming out. Here it is coming out to 41.7. Right, so there is a lot of distance that is coming across between the different kinds of clusters. So let's say I am going with these 5 clusters for time being. So that's how I can look at what are the clusters for each one of them. I can look at the cluster centers, right? You could very well make out which clusters are going more positive, which clusters are going more negative. So age wise, this is a cluster containing highly aged kind of people. So you can very well divide the things across the clusters. You could see how many are falling into each of the clusters. You could see the size of each of the clusters as well. So we are talking about 324, 162, 163. So that's the kind of a sizing we are looking at each of the clusters. Then if I have to really evaluate the performance of the model, I have no other thing to compare, right? It's not predicted versus actuals. There is nothing like that because there is no dependent variable as a part of this model. So we are trying to see how good is our model based on the purpose that I want to put it to. So I want to see how many examples are falling into each of the groups. So I should not get too high or too low in each of the clusters. If that's the case, I don't need to go ahead with that kind of a classification mechanism. And look at the coordinates of the cluster centers. I should be able to see some kind of clear-cut difference across the various groups of clusters in such kind of scenario. The other way I can talk about is, see, okay, now I have created 5 clusters, right? So you append this cluster to your actual data, right? You can very well, now that you have created these clusters, we can very well think of appending this particular cluster to each of the original variable. Right, now that we have 5 different clusters, we can very well think of appending this cluster. So let me take this insurance, let me append it to insurance dollar cluster. I'll append it as, what is that? I have called it as a model 3. So I'll take model 3 dollar, I'll take model $3 cluster. So whatever I'm getting as a part of this cluster, which is the clustering vector I'm getting through cluster, I'm appending it as a part of the new variable called cluster in the insurance. So let me look at the head of insurance just to get a clarity out here. So this is how I am getting the cluster. Some of them are cluster 2, some of them are cluster 4. So we have appended it as a new column at this particular layer. Now I really want to see, I want to do an aggregation of the clusters, seeing whether there is any kind of a clear-cut differences in the charges. Right? I want to really see whether there is any kind of a clear cut difference in the charges across the clusters. So this is where I can very well take aggregate, right, wherein I am taking the charges across the clusters. So I am taking charges tilde cluster, where the data I am taking it as insurance, and the aggregate that I am looking at is the mean. So across the clusters, I am looking at the charges, the average charges. So my answer is coming out that for the cluster 1, the average charge is around 13,000. So I'm not seeing any big difference across the clusters. If you see, cluster 2 probably looks very much on the lower side, right? Cluster 3 and cluster 1, I'm not seeing any kind of a big difference. Cluster 4 looks slightly on the higher side. So I don't see any kind of a big difference across the clusters when I'm going with a 5 cluster solution, right? Now I want to improvise it, seeing if at all there is a possibility that I can use the first model where we have created a 3 cluster solution. So with that, let me try to see, is there any kind of an improvement in the aggregates. Even there I am not able to make any big difference with respect to charges. So the clusters that are typically created with these variables, I am not able to use them for any kind of a business purpose. Even if I am going with the 4 cluster solution that I had, I am not sure that, okay, if you see here, the first and the third clusters, their average charges are much similar. It's only the fourth cluster that is very much on the higher side. So we are not able to differentiate too much between the clusters. Probably we should have tried the T-dot test as well, right? So we can do a T-test, and even we can check out whether the cluster solutions are really statistically significant or not. So that's how we are talking about the real world usage of the cluster. So when I'm talking about improving the performance, so the performance of a clustering algorithm, one, it is depending on the quality of the clusters, right, which is talking about the between the clusters sum of the squares as a percentage of the total number of total sum of squares of the error. Along with that, I am also seeing for what purpose I want to use those clusters. So you can very well integrate the cluster with the data. That is what I have done. For that insurance data, I have added the cluster solution, and I am trying to see whether any kind of a meaningful conclusion, meaningful distinction can be brought about between the clusters, saying this cluster people, they have higher charges, this cluster people have lower charges. Can I really do a differentiation across the clusters? So we can use different kinds of tests across the various groups to really come out with those kind of solutions. So that is what we need to have a basic understanding regarding the clustering process, right? We have looked at all these various aspects. Hope you have got a fair amount of idea in terms of using cluster analysis for creating the groups of data. If you have any further queries regarding the same, you can very well get back to me by giving me a call on the number that I have given below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.